to pass, not only pass, but you also want to do well in the examination in class, the assignments you do in the tutorials are very, very important. And even if you decide not to do the formal grading in the tutorials, you should do the assignments, at least do it privately, do it as best as you can, because this is pretty much indicative of what we expect from you also in class, in the assignments in the course. You cannot come around that. Yeah. Good. Okay, so let's get started. You may have realized yesterday was the announcement on the Nobel Prize in Economics. And some of you may have realized that among the prize winners, there's Joshua Angrist from MIT. We use a textbook, so parts of my course built on the textbook by Angrist and his colleague Pischke. And I mean, they get the contribution. Well, here there's the official announcement for their empirical contribution to labor economics, but particularly on its own causality, identification of causal relationships. So we touched a little bit, of course, in a very, very basic way in the first lectures last week, if you remember. We will do a little bit more on that if we come to instrumental variable estimation. So you see, this is these are very important methodological contributions whenever we want to identify the effect of certain programs or certain measures. Okay, this maybe for some of you makes it maybe more interesting to have a closer look also in the book by Angrist and Pischke, which circulates around these topics. So it's on the one hand a hands-on book, but I mean, they touch topics they cover in their research, as you may have realized, referring to highly cited papers on their own and also of others. So yeah, I think that should give you maybe a little bit of motivation or for what we are doing here and why to learn these things. Good. Okay, nevertheless, we will continue now with pretty basic stuff on ordinary least squares. I do my best to find a good compromise between providing the basics for those who do not have a very solid background in these basics, and for the others, they should not get too bored. Some of you, particularly coming from the Econ Bachelor, they heard all these things, so then just keep it as a fresh up and as a repetition. And for those who haven't done these things, not at all, but I don't hope that there are not too many people who haven't done this at all. There's definitely some students who have not covered this in too much depth. Then basically now this is an indication for you that you have to work hard during the next 2 weeks to catch up on these basics. Good, we're talking about ordinary least squares. I started with that already, and we're talking about the assumptions. The first assumption we discussed already on the linearity of the model. And linear means linear in the parameters, and these are the examples I gave you already. And it does not mean that we cannot use transformations of our left-hand variable and our right-hand variable, as for instance, in this example here or here. Okay, good. A second important assumption is that the regressor matrix is of full column rank. This is, of course, first you need to know what a rank of a matrix is. And what means full column rank? Well, it means that if we have a regressor matrix, that it is not possible that one column, that means one regressor, can be reproduced by a linear combination of the others. Why? Because then this regressor would be redundant, because it would carry exactly the same information as the others together, right? So this is pretty clear that this has to be ruled out. Mathematically, this basically means that we say we rule out, so we just take a sum, a linear combination of the regressors, the regressor columns. So this is a regressor column. This is the column number j. This is lambda j. This is just a coefficient, yeah, a weight. And now we take a weighted sum of these. And I do this for all regressors, but not for regressor number I. Okay, and then it is ruled out. So it must be true that this is not equal to regressor number I, right? So this is now mathematically what I just said. It is not possible that the regressor number I can be reproduced based on a linear combination of all other regressors. Okay, so this is the way how we can write it down. Good. Next assumption is a key assumption as well. This is the strict exogeneity assumption. Strict exogeneity simply means that. So the conditional expectation of the vector of error terms, recall this is a vector. Maybe it's maybe on your slides, if it is printed, then it's easier to see, but this is bold. And bold means this is a vector. This is the vector of all error terms. And the expectation of this vector of error terms, given the regressor matrix, is equal to 0. Okay, this is a compact notation for basically saying that the expectation of any error term epsilon I, given any regressor at any observation. So this basically says I consider any regressor j at any observation I, and it takes a certain value, let's call it v, that's a number, whatever it is. And we say, okay, no matter which value some of these regressors takes, the mean of any error term is equal to 0. So this must be true for all I from 1 to n. That means for all individual error terms. And it must be true for all different regressors 1 to k. Yeah, this is essentially what it means. And what I have written down here is the typical shortcut notation, which is just what you see on the slide. So if you see something like this, then what is behind this assumption is this. Okay, and now what do we mean by this assumption? I just repeat this. In principle, that should be known, but it is really key. So therefore, I just repeat it here again. So the first implication is that the unconditional expectation is also equal to 0, because we can use the law of iterated expectations. So I take the unconditional expectation of the conditional expectations. This here is by some assumption equal to 0. Yeah, this was the assumption we just discussed. And then it's clear the expectation of 0 is also equal to 0. So we see if the epsilons are 0 in terms of a conditional expectation, then they are also 0 in terms of the unconditional expectation. And based on this result, we also can conclude on the covariance between the errors. Again, this epsilon here is the vector of errors, and the x is the regressor matrix. So what you see is the covariance between any epsilon and any regressor. Well, what can we say on that? Well, just exploiting that as we just have shown, that the mean of epsilon is equal to 0. A covariance is nothing else than the expectation of the product between epsilon and x. This is what I told you already last week. Whenever you see such expressions, then you should immediately think of a covariance. Yeah, and now we use the law of iterated expectations, but I use it, so this stands for law of iterated expectations, LIE, and I use it backwards, meaning that I just rewrite this expression now in a slightly more complicated way, which however is the same. Right, I can write this expectation in that way. I mean, using the law of iterated expectations, this here is the same as this one. Yeah, but why I'm doing this? Well, because here I use a conditional expectation and I condition on x. And conditioning on x means that I shut off the randomness in the random variables x. So I condition on them, I treat them as given. And if I treat them as given, then of course I can put out this x here in front of this expectation operator, because this is conditioning on x, right? I mean, this is the nice trick whenever you work with random variables or product of random variables, and you want to shut off the randomness of one of these terms, then you need to condition on it. And conditioning means, okay, you treat it as given. This is exactly what we do with regressors in a linear regression model. Well, we have the data in front of us, but we know these are realizations of random variables. And we take these realizations as given. So that means at this point in time, we condition on this set of regressors, which is available to us in our data. So that means we always have this conditional view on the regressors. Okay? So, and why I'm doing this? Well, it's clear, because now I can again exploit this assumption, number 3, which we just discussed, which says that this is equal to 0, strict exogeneity, which makes the entire product equal to 0. And then, of course, the expectation is also equal to 0. So it means we can conclude that the covariance between the errors and the regressors is equal to 0. And if the covariance is equal to 0, then the correlation, which is nothing else than a standardized covariance, is equal to 0 as well. Okay, so that means the take-home message is that whenever this is true, whenever we assume this, then it implies this, and it implies this. Okay, or you can say it implies this. But of course, if you would assume this, so uncorrelatedness, basically this also has a name. Well, the terminology sometimes differs a little bit, but in some textbooks this is called weak exogeneity. And weak exogeneity just refers to the uncorrelatedness between the errors and the regressors. So if we would now assume weak exogeneity, we would assume this, then we cannot conclude that this is true, because this assumption here is stronger. Strict exogeneity is stronger than weak exogeneity. So weak exogeneity is implied by strict exogeneity, but not necessarily vice versa. Yeah, of course, there are special cases where we also can do it vice versa, but in full generality, we cannot. Okay, so this conditioning on the axis is extremely important, and you will see it now all over the place. And why are we doing this? Well, because we want not to make any assumptions on the distribution of the x's, right? So the argument is that the x's themselves, right? I mean, this is the regressor matrix n by k, and they are stochastic. So these are realizations of random variables. And well, we could say, well, this comes from a distribution. This is a density. Let's call it f, with, say, some mean vector. Let's call it mu of x, and some covariance matrix sigma of x. Yeah, okay, but then the question is, well, what is this distribution? Well, what should we assume for the regressors? Are they normally distributed, exponential, whatever, right? I mean, now it becomes very arbitrary if we want to impose some assumption here. And actually, we do not want to impose some assumption. But of course, the tricky thing is we have a linear regression model, y is equal to x beta plus epsilon. And now if you look on the right-hand side of this equation, there are two random sources. So this is random and this is random. Yeah. And well, the question is, if they are both random, then the question is, okay, what is the joint distribution of these? And then it becomes even more complicated. And this is exactly what we want to avoid, to say something about the distribution of the x's, or to say something about the joint distribution between the x's and the epsilons. And the only way out is that we treat the x's as given. That means we do all our statements, or most of our statements, we do them conditionally on the x's. And this helps us a lot, because then we can keep we can treat the x's as deterministic, and then the only random source in this equation is only through the epsilons, comes through the epsilons. Okay, but if we wouldn't do this, then things would become much more complicated, because then we would need to make explicit assumption here on these f and on these joint distribution. Okay. So keep this in mind. Good. And you see it just here in the next step, when we now talk about the covariance matrix of these epsilons, then we do the same trick. Well, we do not want to say something about the covariance between epsilon and x, coming from these joint distribution. So therefore, we condition on the x's. So we're looking on a conditional covariance given the x's. And this thing is what we call psi. So, okay, this is now just a definition which just says, okay, this is called psi. This is the covariance matrix. The next assumption comes here, that we say, and of course, this is an assumption which then can be also relaxed. It will be relaxed if we work with time series data, which comes then in chapter 3. But in the moment, we assume that the error terms are uncorrelated, which means exactly that. That means this here is the conditional covariance between error term epsilon I, error term epsilon j, and this is assumed to be 0 whenever I is unequal to j. Whenever I is equal to j, well, then this is nothing else than the variance itself, which is of course non-zero. Yeah. Okay. So if we rule this out, then it basically means, well, I can just write it down very clearly. So this is the matrix here we're looking on. So it's a second moment matrix. It's the same as, it's another way of writing the covariance matrix, right? So, I mean, a variance is the same as the second moments as soon as the first moments are equal to 0, right? But the first moments are equal to 0. This is already what we have shown. This was implied by strict exogeneity. So therefore, this is the covariance matrix. Okay. And well, this is a matrix which then looks something like this. So here is epsilon 1 squared, here's epsilon 2 squared, here's epsilon 1 times epsilon 2, here's epsilon 1 times epsilon 2, so it's symmetric, and so on. Okay, that means we have all cross terms, and the off-diagonal elements and the diagonal elements, they cover the squared epsilons. So if we take the expectation thereof, then of course we get a matrix. So, okay, we take the expectation, and then it's a matrix which has a sigma 1 squared here, sigma 2 squared here, the diagonals, sigma 1, 2 here, sigma 1, 2 here. So it's the covariance elements here, okay? This is how the matrix looks like. But under our assumption now, we assume that this matrix is diagonal. So we assume that all the correlations and so the covariances between different epsilons are all equal to 0, which basically means that all these elements of the main diagonal, so all off diagonal elements, so that means they are all equal to 0. So red crosses would mean 0. So in other words, we assume that our covariance matrix, which we called psi, now has a more simple structure. We call this more simple structure D, and D stands for diagonal matrix. So that means we assume that the error term covariance matrix is a diagonal matrix where all elements which are not on the diagonal are equal to 0. So I only put big zeros in here, and the elements on the diagonal, these are the variances. Okay, so this is the assumption we assume here. And well, now comes the next assumption, which even more makes things even more simple. This is assumption number 5, that we assume conditional homoscedasticity, right? Conditional as before, because we condition on x's. So we say the conditional covariance matrix, or the conditional, it's just for a single element, so it's a variance. So the conditional variance of an individual error term epsilon I is equal to sigma squared, and this is true for all I. So in other words, our matrix D now assumes that these diagonal elements are all equal, all identical. And if they are all identical, then so under the assumption that sigma I squared is equal to sigma squared for all I going from 1 to n, then this means I can also write this matrix more compactly as sigma squared times the identity matrix. You all should know what an identity matrix is a matrix which has ones on the diagonal and zeros otherwise. And if we multiply this identity matrix with some constant, then of course we get a matrix where this constant shows up as a diagonal element. So they are all identical. This is all sigma squared, and the rest is 0. Okay, so this is the assumption on homoscedasticity. And it basically says that in a linear regression model, just very quickly, I mean, that should be all known to you. So if we have a linear model, so this is a regression line. So it basically says, okay, that now for each individual points, so that the distribution from which the individual points come from, it's not very nice, this picture. So they all should have the same variances. So what we actually observe are realizations of distributions with similar variances. So what we then can see is, for instance, such a realization of points. So this is the assumption of homoscedasticity. Okay, good. These are pretty unrealistic assumptions, and I mean, the big mistake is that students well remember these assumptions because they are so simple. And later on, if we relax this assumption, then you get the impression that these are then rather exceptions. So as I said already last week, these assumptions here are just special cases, unrealistic special cases. They make life easy to get started with, but if we really look on real data, then, for instance, particularly this assumption A5 is typically rejected. So variances are not identical. So it's rarely the case that we have homoscedastic data. So that means very soon we should know what to do if these variances are not identical. So that in the case of heteroscedasticity. Good. Well, actually, the ordinary least squares estimator has been introduced already. Maybe just 2 minutes on that, because I do not want to entirely skip it. But in principle, all of you should know how to derive the ordinary least squares estimator. So the idea is that I have a hypothetical value, right? I mean, this is the parameter vector, including the intercept I'm interested in. So this is beta tilde. So this is a hypothetical value. This is something I dream up, or I have a rough guess. So hypothetical value of beta. Beta itself is unknown. And well, given such a hypothetical value, I can immediately define residuals. I also put a tilde on top. So this is a definition of a residual. The definition of a residual is always the difference between what I observe and what I predict given my guess or given my estimate or given whatever I use for beta. Yeah? So that means this here is the prediction of yi given beta tilde, and this is what I actually observe. And I also can write this in terms of a vector. So now E is a vector, and then Y is a vector, and then this is X beta tilde. So this is now the residual vector. And the objective function of least squares estimation, this is the objective function, I call it S, is then, as you know, the sum of squared residuals. Okay, so this thing here now has to be minimized. Yeah, and I choose now my beta tilde such that this gets minimized. This is the idea. Okay, and if we want to minimize it, so here I just write the objective function is E tilde prime E tilde. So I just plug in my model, which is y minus x beta tilde prime y minus x beta tilde. This is my objective function. I multiply it out. So this is a little bit of matrix algebra for those who still feel there's some deficiencies here. Use these as a nice exercise. So if we multiply out these two brackets, we have y prime y minus 2 beta tilde prime x prime y plus beta tilde prime x beta tilde. Okay, so, and this is our objective function, and well, we want to minimize this, so we need a first order condition. First order condition is the derivative of this function with respect to beta tilde, and I leave this to you as a little exercise to show that the first derivative, yeah, you can here train to compute derivatives based on matrix and vector functions. In principle, it works the same as if you would operate with scalars, but you have to be a little bit careful with the dimensions. So also this is homework for you to show that this here is the derivative. Okay, and well, this derivative is now set equal to 0. So I put this in red, and by setting it equal to 0, now I have to change the tilde to a hat, right? Which simply means I choose or I find my estimator in a way such that it satisfies this first order condition. And if we solve this, then we get, as a solution, we get our well-known x prime x inverse x prime y, our ordinary least squares estimator. Yeah, good. Okay. So, well, based on this, we define our residuals. So I use the notation E for residuals, and don't confuse this with epsilon. Epsilon, these are the error terms. They are unobservable. And the residuals, however, this is something which is observable because it depends on data. It's exclusively function of the data, right? Because this is y, and beta hat is a function of x and y. So everything here on the right-hand side is known. So the residuals are known. This is E, but the error terms are not known. Okay, good. So based on this, we can, based on the residuals, I can compute the vector of fitted dependent variables. Yeah, so this is what you can interpret as my prediction of y given my least squares estimator. So x beta hat is my prediction for y. And if you now put in the ordinary least squares estimator for beta hat, well, this is just this expression here. This is beta hat. I just put in my formula. Then I can write my predicted y in terms of this function. And this thing here, this is what I call P. And P is a matrix which only is a function of the axis of the regressor matrix. And I call this a projection matrix. This projection matrix plays a very important role. We will see it more often in the course. So what is the projection matrix doing? Well, if you apply y to this matrix, that means you apply this projection here to y, then what comes out is the fitted y. Okay, to make things a little bit, to illustrate things graphically here, I prepared a small picture which tries to explain what is going on here mathematically, but also geometrically. Whenever we talk about these projections, for those who have done my bachelor course, they know this picture. So we have a three-dimensional picture where we have on this axis here, we have y. And here on this axis, we have one regressor, x1. And on this this is a little bit cut. This here is x2. Okay, so we have two regressors. So I cannot graphically illustrate more than two, because then I would need more dimensions. Okay, so now what is this vector here? Or maybe let me start with this. This is my observed realization of y. This is a single data point which is somewhere lying in this three-dimensional room, in this three-dimensional space. Yeah, okay, good. So we can put here, this is y, this is my actual, this is a data point, yeah? And this is the vector which describes y. So now what is linear regression doing? Or in other words, what is a projection doing? Because this is the same thing here. So what we are doing in terms of a regression is nothing else than the empirical implementation of an orthogonal projection. Orthogonal projection means that I now orthogonally, and orthogonally means I just orthogonally project onto the space which is spanned by x1 and x2. Okay, so in this classroom here, say the floor is spanned by x1 and x2. So the floor, and this dimension here, this is y. Okay, and y is the data point here, is maybe the data point, maybe one of these projectors. Okay, and now we need an orthogonal projections. So that means we go upstairs in our building and we look downstairs onto this room from the roof, and we orthogonally project this data point, this projector, down onto this space here. And this is exactly what we do here. Okay, and this is this green arrow. So that means we find this projection here. Okay, so and this is of course a point which is now lying in the space which is spanned by x1 and x2. So, and you can describe this point here is a linear combination of x1 and x2. So we can say that this vector here, the red one, this is now y hat. This is the fitted y. Okay, this is how we explain y, or this is our prediction of the point y based on a linear combination of x1 and x2. So, and how does the linear combination look like? Well, we see here, this little arrow here then is beta hat 1. So this is the coefficient in front of the regressor number 1 times x1. And we can put in here an arrow, and we have beta hat 2, x2 here. So that means the linear combination, which is optimal, is we take this proportion or this weight of x1, and we take this weight of x2, and this brings us then to this point here, and this is y hat. And why is y hat optimal? Well, what is our criterion? Well, the difference between y and y hat is obviously this vector here. This is this distance. Okay. Well, what does this distance mean in terms of our linear regression? What is the difference between y and y hat? Well, I just defined this 5 minutes ago. Well, this is the residual vector. This is E, the green one. And our objective is to make this distance between y and y hat as small as possible, to bring this as close, to bring these points together. Well, this point is given, of course, we cannot change this. We only can change this. But of course, given that we only use a linear combination of x1 and x2, we cannot move out of our space. And our space here is the floor, right? So we only can use points on the floor. And of course, we use that point on the floor, which brings us closest to y, which is the projector. Well, and then this, of course, means this is then exactly the point which is orthogonally just below this point. So that means this point here leads to the smallest distance between y hat and y. Okay, and why does this make sense mathematically? Well, because you also may have learned, I hope you have learned, that the Euclidean distance, so basically the length of a vector, so with these arrows here, this is a norm. Yeah, this is the so-called Euclidean norm. Yeah, I think you learned it in basic math courses. And well, what is it? It's the square root of the squared elements of this vector, right? And in our case, these are the squared realizations of all these n residuals. And this determines the length of this vector. And this is now exactly what we are going to minimize. So minimizing the length of this vector simply means minimizing the sum of squared residuals. And this is exactly what we do mathematically. Okay, so that means now what we see here is that this random variable y can be decomposed into two components. Here is one component, and this is the other component. And these components, they are by construction orthogonal on each other. Otherwise, this point would not be optimal, and then this distance would not be minimized. Okay, this orthogonality is by construction. You will see it also in the formulas in the following. So that means we can decompose our random variable into one component which is perfectly correlated with x1 and x2, right? Because any point here on this floor is, of course, by construction perfectly correlated with x1 and x2, because any of these points is a linear combination of the two, right? So this here is perfectly correlated with the axis. It is a function of the axis. Well, and this is also what we see, because the y hat is x times beta hat. Yeah. Okay, and the other vector is just orthogonal to that. That means this is the component in y which is completely uncorrelated with x1 and x2, because it stands orthogonal to this space. And every point which is orthogonal to this space is obviously not in this space. Therefore, it cannot be reached by any linear combination of x1 and x2. Okay? So, and this is a decomposition you will see during the course very often. And what linear regression is doing is nothing else than a projection of a random vector onto a space which is spanned by regressors. And if we have more than two regressors, then this is not a space, then it's just a plane, a hyperplane. But the intuition then, of course, cannot be worked out graphically anymore, but the intuition is the same. Okay? So, and this is this y hat. This can be now also written, as we just have shown, in terms of a projection matrix, projection matrix times y. So it's p times y. And sometimes we want to be very precise on the p, then we do a little x on the p. I also do this here. We also may do this here. Yeah. So I put an x here to make clear that the projection matrix is defined in terms of axis. Because if here I just write, maybe that's a little bit, or this is definitely a little bit imprecise when I write this is a projection matrix. This is correct if I write this is a projection matrix. But if I write px, then it is the projection matrix, the only projection matrix based on the axis, right? Because it's always the question on which space do we project the y, right? We also could find some other space based on other regressors. Yeah, so we have to be clear on about what the space is on which we project. Here it is, I call it x, and then it's well defined. Then I find the fitted y based on a projection of x, based on a projection of y on x. Okay, good. So keep this in mind. This intuition, also this geometric interpretation, because it is quite helpful. It is already helpful on this slide, because now, without going into much detail, I think most of these expressions are quite intuitive. So here now we look on the residuals. And the residuals are, I mean, this is just a definition. I just write it here again. It's y minus y hat. But y hat, as we just learned, is p times y. Okay? So therefore, I also can write it in this term. Yeah? So this I here is an identity matrix. So identity matrix times y gives y, and p times y gives py. So it's the same thing. But now I can formulate this matrix here in the brackets. I can give this matrix a name, which is called M, which is just identity matrix minus P, right? P is here, so it is this expression. I just substitute it in. And this matrix, what is this matrix doing? Well, if I have a vector y and I confront this vector y with M, so in other words, more precisely, I multiply y by M. Yeah, what do I get? Then I get the residuals based on the underlying projection. Yeah, so if I'm a little bit more precise, I put a little x here. Maybe I should do this in the future, and the x here, and I put also an x as an index on the M. And then it's clear what it means, because then it basically says, well, if I take the vector y and I multiply it, I pre-multiply it with these mx, then it gives me back the residuals based on a regression or projection, if you wish, of y on x. And therefore, we call this thing a residual maker. So this matrix M has some nice properties. The same is true for P, by the way. I will not prove this, but we will use it from time to time. Therefore, you should keep this in mind. First of all, so I mean, 3 key properties you really should keep in mind. First of all, the M matrix is orthogonal to X. Yeah, where does this come from? Well, in my picture, it basically says, well, the residuals here by constructions are orthogonal on the space by X, and M is a function thereof, right? M produces these residuals. That's the intuition. We also can mathematically show it that M is orthogonal to X. Yeah, that's what it says here mathematically. And the 2 other properties are very easy to memorize. First of all, the transpose of M is equal to M, which means we can be quite sloppy with respect to the transpose. We also can forget it, and it's not a mistake. It's the same thing. And if I multiply M by M, I still get M. Also, this is a nice property. So these are very special matrices. The same properties are true for P, by the way. Yeah? So then I can express a relationship between the residuals and the error terms. Right, and I made clear that these are the residuals. They are observable. I can compute them. The error terms are unobservable. Okay. So first of all, well, just plugging in this expression from above. Well, this is just my model. This is Y. Yeah, and E is computed as M times Y. So I also can write it in this way. Yeah. So but then just exploiting that M times X is equal to 0. This was the property I just mentioned, yeah, which makes this product here equal to 0. So it drops out. So the only product which remains is M times epsilon, and this is what you see here. Yeah? And now comes a question which I always ask at these points, and some of you may know this already. So the question is, well, given that here I have a relationship between residuals and error terms, and given that M is fully observable because M is a function of my data, so I can compute it. I can compute this matrix M. Yeah. Why can't I? And so I see that this is observable. This is observable, and then of course, in principle, that should also be observable, because why is it not possible to solve it for epsilon, but just to write inverse of M times E? Yeah? So why can't I solve this equation for epsilon, and then the epsilons, my error terms, become observable? Right? Why does this, or what is wrong with that? Right? This is observable and this is observable, and then this also must be observable. What is the answer to that? Thank you. Exactly. The answer is M is not invertible. So this thing here does not exist. That means I cannot do this step. So our intuition, it still remains. Error terms are unobservable, and they are still unobservable, but the residuals are observable. Yeah. So I can express the residuals in terms of the epsilons, but not in the other way around. Yeah. Good. So some numerical properties of ordinary least squares. A numerical property is a property which holds by construction of the estimator. Therefore, we call it a numerical property. Yeah? So the first one comes from the first order condition. The first order condition, I gave you this as a little homework to show that the first order condition is this one here. And I give you this now as an additional homework just to show, I mean, this is, you just have to rearrange terms and then to show that this is the same as x prime e equal to 0. You just put in the definition of a residual into this equation, and then it's the same. So that means the first order condition can be also expressed in that way. So if it can be expressed in this way, then it means that it must hold by construction, because we constructed our estimator such that this first order condition holds. So it's not a surprise that this is a numerical property. So this must hold by construction. And this has some, and this means, of course, that each regressor, each column in our regressor matrix is orthogonal to E. Yeah? And also an implication of this result is that our projection is also orthogonal to the residuals. If you look on my picture, that should be also clear, because this here is my prediction, my projection. And of course, it's a function by construction of x1 and x2, because it's a point in my space. But this space is, of course, by construction orthogonal to the residual vector. Therefore, the residual vector must be orthogonal to y hat. So geometrically, this is clear. Mathematically, we also can show it. Yeah. Good. So, and well, if we just use this property and we assume that the regression equation has an intercept, if it has an intercept, then it simply means that one of the regressors, of course, typically we take the first one, that the first column in our regressor matrix consists only of ones. Yeah, so that means this thing here is 1. Yeah. So if it is 1, we also can drop it out from this expression, and what it remains is here a sum over the residuals, and this of course is equal to 0. Okay, so by construction the residuals must sum to 0. Alternatively, if you wish, you also can multiply both sides of the equation by 1 over n here and here times 1 over n. Of course, on the right hand side it does not change anything, so I can skip it again. But if I put a 1 over n here, I mean, this is just an average. Yeah? No matter whether you look on the sample average or no matter where you just look on the sum, it is 0. It must be 0 by construction. Yeah. So, I mean, this is something which cannot be tested, or it's useless to test this because it must hold by construction. Yeah. So this is something which is useless to test. Sometimes I ask for this in the exam. So typical multiple choice question. Good. Okay. Fish-Waugh theorem. Well, this is connected to something we have discussed already. And before looking on this theorem directly, or let me just explain it here intuitively. I think this is easier. So assume we have a model which consists of 2 blocks of regressors. So X1 is a regressor matrix. This is a certain set of regressors, times beta 1, which is the corresponding vector. And this is another block of regressors. Now you also can make things easy if you wish, and then you can say, well, this is a regressor number 1 and it's a regressor number 2. Well, it doesn't matter whether this is now a matrix or a vector. What is important is we have 2 sets of regressors in our model. And well, of course, our estimator is beta hat. This is the vector which consists then of beta hat 1 and beta hat 2. You remember, I discussed this last week already. Now the question is, well, how can I back out an estimate separately only for these values or separately only for these values? So the question is, how can I identify the direct effect between, say, regressor, let's take the second one, regressor number 2. I'm interested in the effect between x2 and y, but I do not want, or I want to control for the correlation between y and x1, and also the correlation between x1 and x2. Okay? So generally we have 3 random variables. They are all correlated with each other. Yeah? And we want to identify now, we want to identify beta 2. And beta 2 gives us the exclusive effect, the so-called marginal effect. Yeah, so the effect of a marginal change in x2 on y. Now, this is in many analysis a very interesting quantity. So I would like to identify the marginal effect of a change of the regressor x2 on y. And of course, this marginal effect is quantified by or is captured by beta 2. Okay, so how can we do this? Well, the problem is I have this interaction. There's also some correlation between x1 and x2. That means a part of the total effect from x2 to y goes through x1, because there's a correlation between x2 and x1, and there's also correlation between y and x1. Yeah? But I want to switch off these connections. So in principle, I would like to take a ceteris paribus view. So given I would be able to fix x, so keep x1 constant. So x1 is not allowed to move anymore. So I want to shut off the randomness in x1. So what is then the effect in y if I change x2? So I want to have the exclusive effect of x2 on y, right? This is captured by beta 2. So how can we compute this? Well, of course, I mean, it is this beta 2. Your answer now would be, well, just take this value here and we are done. Yes, but I also would like to show you how to compute this term here directly, because here this is only implicitly because it's part of a vector. And then, of course, I have to squeeze out these elements of this vector. Of course, I can do this, no problem. Yeah, but I would like to have a direct analytical expression for this beta hat 2. Yeah. So now I can just make use of my nice results which I produced before. So what do we need to do? Well, in principle, I would like to shut off, or to how should I express it? I would like to eliminate all effects in y which come through x1. Okay, so how can I do this? Well, I do a regression. I regress, first of all, y on x1 only. Okay, so as we just have learned, I can always split off y into a part which is perfectly correlated with x1 and a part which is perfectly uncorrelated with x1. Okay? This is exactly now this orthogonal decomposition. And I'm interested now in that part which is perfectly disconnected from x1. Okay? So how do I get this? Well, remember the picture we have drawn? I take the residuals. So I regress, remove it. I regress y on x1, and I take the residuals from this regression, because this is then by construction something which, this is then by construction that element in y which is uncorrelated with x1. Right? This is exactly, just take the intuition here. Right? The residual always carries that part in y which is completely unrelated with x1 and x2. Okay, so now I use regression basically as a technique, and actually this is done very often, to decompose a random variable. So, and I use my formula from before. So regress y on x1 and compute residuals. So how do they look like? Well, I just use my M formulation. So, and I call it M1 M1 means it's a projection. This is this residual maker matrix based on X1, yeah, and multiplied by Y. So this is the residual. So, okay, maybe I just write it down. So this is the residual maker, this identity matrix minus X1, X1 prime, X1 inverse, X1 transpose. Yeah? This is M1. So this gives me the residuals. So, and this gives me now that part in Y, which is disconnected from X1. Okay? Good, then I do the same. For X2, I regress X2 on X1 and compute residuals. How does this look like? It's M1 times X2. So this is that part now in X2, which is disconnected from X1. So now in principle, these two components here, these residuals, they cleaned off all components coming from X1. And now I can do the last step. The final step is I regress these two things on each other. This residual, so in some sense, the cleaned Y on the cleaned X2. Yeah. Instead of just running a regression of Y on X2, that would give me the wrong result, because then all these effects of X1 would be still included. So I clean the Y and I clean the X2, and then I regress the two elements on each other, the two vectors, or, well, this here is a vector, sorry, this is a vector, and this is a matrix, if X2 is a matrix. Yeah? So it's just a usual linear regression of these cleaned variables. And this gives me beta hat 2. Yeah? And now I can write beta hat 2. I just use the ordinary least squares formula. X prime X inverse, X prime Y. But the X now is, of course, this cleaned X. So the X is not just X, it is M1 X2. So if I would need to write X prime X, now I would need to write X2 prime M1 prime M1 X2 inverse, right? I mean, this is X prime, the X prime X part. Yeah? So X prime X inverse times X prime Y. So X prime is then X2 prime M1. And the Y itself is the cleaned Y. The cleaned Y is M1 times Y. Okay, so, and then we have this nice result, what I discussed before, that these residual makers, no matter whether I forgot the transpose or I put it in, it's the same. And if I multiply them with each other, then it's still the same matrix. So this is also M1, this is also M1. So that means I can directly write these as X2 prime M1 X2 inverse times X2 prime M1 times Y. Okay. So and now we see something interesting. Well, if you look now on this expression here, then you see that basically this is the same as if I would just do a regression. So this expression here tells me that it is sufficient to clean only X2, right? Because I mean, the Y is still the Y. The X is now, the X2 here is cleaned by the M1 here and here. So mathematically, it's the same. So actually, it means that this is totally the same as if I would just, so I put it in here, as if I would just would do a regression of Y on M1 x2 instead of the cleaned y. Yeah? And why is this? This is due to this orthogonality of different vectors, and I don't go into details here. So the take-home message for you is to understand the implications of this Frisch-Wahl theorem. And the Frisch-Wahl theorem is exactly what I described here, because it says if we are interested in an exclusive analytical expression for beta hat 2, of course we can do the same also for the other one, but now let's stick to that one, the second one. Yeah, what we need to do is we need to run a regression of y on this x2, but this x2 must be cleaned of all effects coming from other regressors, in this case x1. So do a regression in terms of cleaned values, and then we get directly that. Yeah? In the other way around, if we're interested in this, then of course we do a regression of y on x1, but then we need to clean the x1 by effects coming from x2. Okay, this is the Frisch-Wahl theorem. It is, we will use it again when we come to panel data. Yeah? It is sometimes just very convenient to derive certain statistical relationships, and sometimes it's also convenient to work with our data if we want to clean out certain effects in our data. Yeah? Then we can do this basically by running these linear regressions before, and then we run the final regression. This is the final one here based on cleaned data. Okay, so this is basically what you see here on the slides. On the slides, however, I just realized that there is a mistake because in the way I have written down it here, it should be exactly the other way around. So please just interchange these two expressions. So I made there was a typo in here. It's exactly the other way around. Yeah. Okay. Good. This is the Frisch-Wahl theorem. And of course, the connection of the Frisch-Wahl theorem is, we implicitly discussed this already. Let's see whether I find it. Here, it's that one. It's the same thing. The only difference is here I explained it in terms of population moments and just in terms of a very simple setup. Yeah, a more simplified setup, just assuming that it's just a single regressor. Here, now I explained it for an entire matrix, but I mean, this is not a major difference. It's only a difference in terms of notation. But the major difference is that here I explained it in terms of population moments. It's a population covariance, it's a population variance, and this is a population regression parameter. And what we now did, we did basically the same thing, but with hats on top. That means all these population moments are now replaced by their sample moments. This is what we just did. So it's the same thing. Yeah. Good. So are there questions? At this point? Yes? This theorem is useful, for instance, well, we often have the situation that we are economically interested in one or a few parameters. So let's assume we are economically interested in beta 1, because we want to test effect of a program or causal relationship between x1 and y. Yeah? Okay, so we're economically interested in beta 1. Nevertheless, we need to include additional controls, right? Because they belong to the model. They are all drivers of y. So we cannot just skip them, because then we would get a bias, an omitted variable bias. So we need to keep them in the model. But we just keep them in the model, but we are not interested in beta 2. No? And sometimes it can be the case that this x2 here is very high dimensional. So actually that we have to estimate many, many parameters. And the example I'm referring to in a panel setup is, in panels, some of you know this already, we often need to control for fixed effects. Yeah, individual specific effects. That means we need to estimate a parameter, one parameter for each individual. An individual could be a person, a household, a country, whatever, right? And if the cross-sectional dimension of our data is huge, that would mean that we would need to estimate many, many parameters, right? And the traditional argument for the Fréchois theorem to be, this was introduced in the 60s, right? And in the 60s, it was really hard for people to invert matrices. And imagine that this is a very high dimensional matrix. In order to compute the ordinary least squares estimator, right, we need to invert this matrix. So we need to invert x prime x. If this is a huge matrix, then this is computationally hard. Nowadays, this is not so much a problem anymore, but I mean, if the x is really huge, can be also a problem nowadays. And for that, this theorem is very useful, because it gives us a way to exclusively compute beta 1 without the need of computing the beta 2. But still, we control for the effects of x2 in the model, so we don't make any mistake. Yeah, that's the main application. And this is also how we deal with these in the panel setup. Okay, more questions? Good, then let's move on. The mean and the covariance of ordinary least squares. The first is the unbiasedness property. This is one of your exercises, one of your assignments in the tutorials, and therefore, of course, I will not show this here. This is something you have to deliver, and for some of you, this is trivial. For some of you, this is maybe not so trivial. Yeah, I mean, this is exactly now also to show you a little bit what we expect from you, what your knowledge at this point should be, and if you realize that you still struggle with these things, then it's time to catch up. So do this first assignment, yeah? And in this first assignment, you have to show that under this assumption A1 to A3, yeah, the ordinary least squares estimator is unbiased. Okay? So an implication of this property is, of course, if this is true, then it implies that the estimator, okay, let me use blue, that the estimator is also, that this is also true unconditionally, because we can use the law of iterated expectations, right? So if I just put an expectation around that, yeah, and I do know that this here is equal to beta, well, this is just the theorem, then the expectation of beta is equal to beta. Yeah? So if this is true conditionally, then it also holds unconditionally. Okay? So the second result, and this is also on the assignment, is to show the variance covariance matrix of the ordinary least squares estimator. Of course, given the axis, you see here it's very important. So we treat the axis as given. Yeah? And then, of course, if we treat them as given, then this term here on the right-hand side, this is all given. Yeah? So this is the variance covariance matrix under assumptions A1 to A4. remember the assumption A5 was the assumption on homoscedasticity. That means this form of the covariance matrix holds if we assume that the covariance matrix, we just go back, the covariance matrix has such a form. Of course, it is diagonal, but these elements here can differ. This is what we call heteroscedasticity. Yeah. So, I mean, this is the first important result. Important in the sense that it makes things more realistic, because, as I told you, most data is heteroscedastic. So therefore, we would like to derive the variance covariance matrix of our estimator without assumption A5. That means without relying on homoscedasticity. Yeah? And this is the covariance matrix. If we then additionally impose the assumption A5, then things become easier. Well, because then these D matrix, I can just put it in here, but I mean, you should do this as an exercise yourself, right? I mean, but that's pretty obvious. If we impose assumption A5, then this D matrix is sigma squared times an identity matrix. Yeah, so that means we can then put the sigma squared in front of the expression because it's just a proportionality factor. And then you would have here an identity matrix, x prime I times x. Well, multiplication by an identity matrix gives back the original matrix. It's like multiplying by 1. So we also can leave it out. Yeah. So that means this expression here is nothing else than x prime x at the end, which cancels out against x prime x inverse. And what is then left over is this x prime x inverse together with the sigma squared, right? I mean, so the term collapses, this expression collapses in case of homoscedasticity to this term. Okay, so it's your homework to prove this. Yeah, your assignment. Therefore, I don't do this here. So let me point out, this is the population variance. I call it V. Population variance means this is a theoretical variance, and it still depends on some unknown parameters. Here it is just one parameter. Here it is an entire matrix of parameters, a diagonal matrix where the diagonal elements can be different. So in the extreme case, it would be the case that here we have n individual parameters to estimate. For each observation, one parameter. Yeah? So how can we do this? So let's start with the more simple case. And the more simple case is if we just need an estimate for sigma squared. Well, there we can use the well-known result, which I will not prove here. We can show that the sum of squared residuals, so sometimes I use this as an abbreviation, so sum of squared residuals. And the sum of squared residuals, please be aware, this is, first of all, what is it? It's the objective function we minimize in our least squares regression, right? I mean, this is exactly the thing we are going to minimize. So we find our estimator such that this thing here is as small as possible, okay? This is the first thing you should remember whenever you see a sum of squared residuals. The second thing is, it's a random variable, right? Because the residuals are a function of our data, of y and of x. So it's a random variable. If it is a random variable, then it is a distribution and it has an expectation, okay? And here we compute the expectation thereof, but we make life a little bit easier in the sense that we condition on x's, so we shut off the randomness in the x's. So the randomness then only comes through the error terms. Okay, and then we can show that the conditional expectation is just n minus k times sigma squared. And sigma squared is the error term variance. from which we assume that it is constant over all observations. That's the assumption of homoscedasticity. So that's an important result, and this allows us to construct an estimator which just takes these sum of squared residuals and divides it by n minus k. And now if I compute the expectation of this, and then of course the expectation of this, and I just plug in this, what we get out is then of course sigma hat squared. So this result, which means that this estimator I've now constructed here is unbiased under our assumptions, of course. Yeah. So I can find an unbiased estimator of sigma squared. Yeah. And what is it? The sum of squared residuals divided by n minus k. Well, that should be very intuitive to you, because what is this? Right? If we just write down this SSE divided by n minus k, I just write it down here exclusively as a formula once again, right? It's, of course, it's already a slide, but I want to stress this point. So what is this? Well, recalling that the mean of all these residuals, or the average of these residuals, is equal to 0 by construction. It's a numerical property. Yeah? That means I could also write this, oh, sorry. Oh, okay. I also could write this in that way, right? Because what I have included here, this E bar, this is the sample average of the residuals. And the sample average, we just discussed this before, is 0 by construction. So I also could leave it out. But why do I put it in here? Because I would like to give you the intuition that this is nothing else than a sample variance. Right? The only little small thing what is different to the sample variance, you know, from statistics is that here we have a k instead of a 1. And k is the number of regressors. And if we only would have one regressor, meaning only an intercept, then this is exactly then it's nothing else than the sample variance based on our residuals. Okay? And I mean, I think it is super intuitive that you find your estimator for this unknown error term variance as the sample variance based on the residuals. So there's a lot of intuition behind this formula. Yeah? I hope. Good. Once we have an estimator for sigma squared, well, then in the case of homoscedasticity, we can just plug it in. And now I have my estimated covariance matrix of the estimator. Yeah? And this is, of course, an important quantity which I need to assess the precision of my estimates. Yeah? Because, I mean, we just go back. This result here, I mean, this is a result which students always remember. But of course, what does this result actually mean? Well, if this here is the distribution of my estimator, right? So this is f of beta hat. F is just a density, right? Beta hat is a random variable. So what does this result mean? This means, okay, that on average, right, the expectation on average, the distribution is centered around the true parameter. Yeah? This is beta. But of course, the variance then tells me how far away I can get from this true parameter. Yeah? Therefore, it is very important to know what the variance is, and therefore I need an estimator for the variance. So, in the case of heteroscedasticity, things are a bit more complicated, but I will not formally prove the things, but there is a key result which has been developed already in the 60s by a German guy called Eicker, and in statistics, and then it has been introduced in econometrics by White nearly 20 years later. So we see that statistics is often, not always, but often ahead of econometrics. And so the most acknowledgement goes to White, but actually, therefore, I also call it, and many people call it that way, it's the Eika-White estimator. So what is the Eika-White? This is where the E and the W stands for. This is now an estimator for this matrix here. Yeah? And what they have shown is how to construct now an estimator for this quantity in here. Yeah, and why is this complicated? Because this D is a diagonal matrix which contains many, many unknown parameters, right? It's not just a single parameter, as in the case of homoscedasticity. In principle, we can have for each observation an unknown parameter. So it's not so easy to construct a useful estimator. With useful, I mean a consistent estimator for this expression here. But they have shown this. I will not prove it. They have shown it that actually we can compute it in this way. I just give you a slightly different notation of the same thing, which is maybe a little bit easier to digest, right? And this is so this looks like this. So this is x prime x inverse x prime d hat x and x prime x inverse. Okay, that's very intuitive that we are now replace d by a d hat. And what is this d hat? This d hat is also, not surprisingly, a diagonal matrix, and it's a diagonal matrix of, also that is very intuitive, of the respective squared residuals. Now, so this is just a shortcut notation for a matrix which looks like this. So it has E1 squared here, and it goes down to En squared here, zeros, zeros otherwise. Okay, so, and this notation here is the same as the notation here. Yeah? For those who still have a little bit of problems of understanding the difference between an inner product of matrices and an outer product of vectors. Yeah, here, this is then a little homework for you to verify that this is the same as this. Yeah, and this is of course easier to understand. So what does this mean in practice? It means that at first place, we need to estimate our model, right? Step number one, we estimate our model. We estimate y equals x beta plus epsilon, and I produce OLS. OLS gives me an estimate of beta hat. Okay, so this is my estimator. Then in step two, based on this estimator, I compute the residuals. So y minus y hat. So y minus x beta hat, I just plug it in. I have the residuals. Okay. Then in step three, based on the residuals, I compute the matrix d hat, because I just plug in the squared values on the diagonal. Okay. And in step four, I plug in the d hat into the formula above, and this gives me my estimated covariance matrix under heteroscedasticity. So, and this is the standard procedure. Yeah. So I really stress it here. This is the standard thing you should always do, because you have rarely the case where you have homoscedasticity. Yeah. This case here, this is just a special case. This is a rare exception. This is the standard case. This is the standard thing you need to do. Therefore, I introduce it here already as early as possible. Good. And we have to stop here. I still give the Zoom people, but by the way, I also give you now the possibility to ask very urgent questions. And then the Zoom people also can directly ask a few questions here. But please wait a few minutes. No urgent questions. Okay, we see us on Thursday, then you can ask questions.
Recording stopped.